Prova, prova. Can you hear me? Very good. So let's start this long last session with Elena Bertola.
Yes.
On tracing agent feedback at cosmic noon, please.
Okay, can you hear me? Okay. So good morning, everyone. My name is Elena Bertola. I'm a third-year PhD student at the University of Bologna. And as you might tell by the names of my supervisors, I was born an X-ray astronomer studying high redshift ultrafast outflows. Then, for the second part of my PhD project, we started a collaboration with Mainieri and Harrison and their collaborators, trying to assess the effect of agent feedback in the molecular gas content of high redshift AGN. So it wouldn't be an AGN feedback talk without a slide like this one. We've seen various versions of both plots in the last days and especially today. But basically, the reason why we care about agent feedback is that we need it to explain the behavior of galaxies during their evolution, and also how their properties correlate with the properties of the AGN. The question that we want to answer is, however, how the AGN can actually affect the evolution of their host galaxy. So basically, how can they affect the star formation activity of their host galaxy? And one possible way is that they might act on the fuel of star formation, which is the molecular gas reservoir of the hosts. However, as we already heard from Federica's talk and previous talks, there is no consensus between what we see in low redshift and high redshift samples, meaning that regarding the low redshift universe, AGN are usually found as indistinguishable from non-active galaxies. As you can, for example, see here we have a proxy for the star formation and a proxy for the molecular gas mass. And as you can see, both active and non-active galaxies populate the same relation. While when we move to higher redshift, AGN are usually found to be CO depleted. For example, this is the result by Biscuit et al. 2021. They find that AGN hosts are usually CO depleted by a factor 4 with respect to main sequence galaxies. However, there's a problem when we study high redshift AGN, and that is that high redshift AGN are usually pre-selected by based on their high luminosity, and also because they are usually targeted as good candidates for showing AGN feedback. So to field while regarding the low redshift universe, we have a much better sampling of the lower luminosity end of our AGN. So to fill the observational gap between low redshift and high redshift studies, these two surveys, XIV and SUPER, were conceived in the, let's say, recent years. And they both share the aim of studying the effect of agent feedback traced in the O3 line on their host galaxies. And they span different ranges in redshift and bolometric luminosity. And actually, this plot is from 2018, but the XIV sample was increased in the recent years and is now reaching also lower bolometric luminosities. The super collaboration found a very important result, which is that when we include also regular AGN in our high redshift samples, we don't find a very significant trace of CO depletion in our AGN hosts. In fact, super AGN are only found to show hints of CO depletion when we narrow down the sample to the highest, to the high mass end and to the high far-infrared luminosity end. So the project that we started a few months ago basically has the aim of increasing the number of regular AGN that are studied in terms of agent feedback in the high redshift universe. And to do that, we took the XIV survey catalog and we cross-matched it with the ALMA archived, and we selected all of those observations that were taken in band 3, 4, and 5. And that is because those are the bands that allow us to target the lower CO, lower excitation CO transitions at the redshift of XIV AGN. In our sample, we have 30 AGN, 7 are shared with super, and some of them are, let's say, famous high redshift AGN, for example, the brightest in the aspect survey, the 2 XIV AGN that Federica told us about before, and also famous XIV, the 2028, and GMAS 0953. So, nope. Okay, sorry. Regarding our data analysis, the aim of the ALMA analysis was to retrieve CO-based total molecular gas masses for our targets. However, since our data sample is based on archival data, is heterogeneous both regarding the CO transitions that are targeted and also regarding the angular resolution. In fact, we span a wide range of angular resolutions. For that reason, we imaged our targets
on the offset from the main sequence, essentially.
Yeah, that's something that I wanted to do after the conference, taking the so computing the gas fraction, taking the results from Genzel 2015 and Tacconi 2018 to see if we see something that is different, like from what we find here, or also by the other analysis.
Okay.
Thank you.
So there was another question, I guess, but while Giovanni has his curiosity, I ask the next speaker to go to the stage, and so
I'm confused. How is this 2-3 sigma difference in the super survey between the CO322? The histogram there is defined, because it looks to me that the two populations are completely different. So if you use the error on the mean, it's much more than 2-3 sigma. No?
The difference here, so these are the, so this is a tongue twister. The priors of the posterior marginalized distribution, this comes from Bayesian analysis. And what we find is that here they seem different, but they are actually at 2 or 3 sigma. They're not so much different than that.
Well, all right. You can discuss later on the statistical significance of any difference between these two distributions.
Yeah, because it's going to be very long. Thanks.
Let's then get speaker again. So the next speaker is Daniele Ribaldi with Lemmings and the email Radio Legacy survey.
2 minutes. Hello everybody, I'm Ranieri Ribaldi, and today I will not speak about feedback, but I will show you some results from a radio legacy survey of nearby galaxies with eMERLI. The identification of an AGN of an active black hole depends on whether we are not able to detect any signature of accretion or rejection from supermassive black hole. So this can be quite simple for our luminous quasars, but can be very hard for a low accreting AGN, a low luminous AGN. And this has a strong implication of our understanding of the AGN phenomena, because our knowledge is completely biased. Our knowledge about AGN phenomena is biased towards massive, bright, luminous, unobscured galaxies and quasars. So this leads to an impartial understanding of the phenomena. That's why there is a tremendous need to go to low luminosity to detect active black hole. And radio observation provides a wonderful tool to identify and isolate radio emission at the center of galaxies associated with the active black hole, thanks to the long baselines array, and detect AGN at accretion rates much below than those detectable in other wavelengths. So why we need to care about low luminous AGN? Low luminous AGN are the most common AGN in the universe, so they are representative of ordinary black hole accretion, rather than quasar, which are rare and flickering. The low luminous AGN are typically in a sort of quiescent galaxies, so they allow you to study the triggering mechanism. And also, since the AGN don't outshine the galaxy, allow you to separate much better the property of the host and the property of the nuclear property, the property of the nucleus, in order to study them separated in order to study the possible convolutional link. And also the low luminosity AGN allow you to constrain the luminosity function at low luminosity, and low luminosity AGN are also typically in low mass black hole, black holes, so they can help you to constrain the black hole mass function and the occupation fractions of black holes at low masses. These two parameters are a fundamental ingredient to set up scaling relation and cosmological evolution models of galaxy and black holes. On the right, you have a luminosity function, one of the deepest radioluminosity function in the local universe, provided by Nagar 2005 at 15 gigahertz, which goes down to the 18.5 watt per hertz. This was the best so far of the local universe. But that's why Lemmings comes. Lemmings, which is a legacy Merlin multiband imaging of nearby galaxies, aims at studying the AGN, so a census of nuclear activity at low luminosity, so really at low accretion rates in the local universe, where we have a better linear resolution of to probe the accretion and ejection phenomena. And the observations are in L-band, C-band, so 1.5 and 5 gigahertz with the Merlin, with resolution of tenth of milliarcosecond and sensitivity of tenth of microjansky beam. The shallow consists of two tiers. The first one is the deep sample, the shallow sample, which is basically a snapshot of nearby galaxies, and the other is the deep sample, which consists of dedicated deep observation of scientifically interesting targets like NGC 4151, M82, M51, and so on. So on the right, I show you the range of luminosity that Merlin legacy survey is going to probe down to Sagittarius A star luminosity. Let's focus now on the shallow sample. The shallow sample consists of a complete sample of optically bright galaxy from the Palomar sample, Ho et al. 95. So they are optically selected with no radio bias, include active and inactive galaxies. So we have liner Seyferts, star-forming galaxies, and absorption-line galaxies, which are passive elliptical galaxies. It includes 280 galaxies within 100 megaparsec typically, and we have full multi-wavelength coverage with HST, Chandra, JVLA, Herschel, and Spitzer. So plenty of data to analyze and to diagnose the nature of the accretion of the center. All the observations are done with the Merlin, which is an SKA pathfinder, which consists of 7 antennas spread across the UK, with baselines of 220 kilometers, which reach a resolution of tenth of milliarcosecond. All the observations are done and published into my papers. Here I show you some example of radio structure we are able to resolve down to a parsec scale from a simple core of typically 50 parsec down up to kiloparsec scale jets or extended structure from star formation. 45% of the sample has been detected. Liners and Seyferts are the most detected ones, not surprising. So then I extracted the radio core component, which is the center of the galaxy where the black hole is supposed to be, and I convert it into luminosity, and the luminosity goes between 10 to the 34 to 10 to the 40 erg per second, which corresponds to 17.6 watt per hertz. So a factor of 100 from Sagittarius A luminosity. We are aiming to go down to a factor of 10 with the C-band observation. This is the distribution of the luminosity for the different optical classes. Liners and Seyferts are the brightest, not surprisingly, but the most important result is that we are able to detect evidence of activity and jets in star-forming galaxies, so galaxies which are supposed to be inactive, and also in black hole, in galaxies with black hole masses above 10 to the 6.5 solar masses. Thanks to my team, we at home, we are able to set this kind of diagnostic panel where basically we are trying to understand the activity, the presence of activity in nearby galaxy with a census of nuclear activity in the local universe. So here on the top we have the distribution of the the detection rates in bins of black hole masses. As you can see, the fraction increase as the black hole mass increase. This is nothing surprising. So it's telling you that larger the black hole is, higher is the probability that the galaxy is the galaxy hosts an active black hole. And on the bottom here, the distribution of the radio core luminosity as the black hole mass increase. And we found an interesting result. At higher black hole masses, above 10 to the 7, we found a sequence of active galaxies. So the radio emission is attributed to the phenomena of accretion-related phenomena at the active black hole. So it could be coronal winds, jets. Remember the talk from Francesca Panessa a few days ago. And at low accretion, low black hole masses, so about 10 to the 6, the sequence flattened. There is a plateau due to the main contribution of star formation, which is becomes the main source of power in these galaxies. So at this break, we found two different populations. Then we have Chandra data, which are better proxy than to study the accretion states in galaxies. So we have Chandra data from archive and from new data in the 210 keV band. 70% of objects have been detected, and for 1/3 of the sample, we are able to also have a spectra. This is an example of the X-ray spectra. We extracted the 210 keV fluxes and luminosity. Liners or Sieverts. Oh, nothing yet. Liner Sieverts are the most detected one. On the right, I show you the distribution of X-ray luminosity for the different optical classes. Liners or Sieverts are the brightest, of course, from 10 to the 36 to 10 to the 42 Hertz per second. Here I show you the X-ray luminosity versus the black hole mass for whole sample with different cuts of Eddington ratios. The liners typically have low accretion rates or low Eddington ratio, which goes between 10 to the 4, 10 to the minus 4, 10 to the minus 6, which is really, really low. And Sieverts higher, typically 10 to the minus 1 to 10 to the minus 2, 10 to the minus 3. So this dichotomous distribution of Eddington ratio is not surprising, something we already know. It is typically interpreted as two different regimes of accretion. Liners are powered by radiatively inefficient accretion disk, ADAF type, and Sieverts by standard accretion disk. So let's now combine the X-ray information we have with the radio morphology we detected with Merlin. So this is the panoramic view of the nearby galaxy universe. So Sieverts are powered by a standard accretion disk, but they have two different types of radio regimes. At low accretion rates, so below 10 to the minus 3 typically, the jets appear typically core brightened and are able to produce, there is interpreted as a sort of subrelativistic jet. At high accretion rate, the jet appear, the structure appear more edge brightened, and the radiation pressure of the disk is able probably to blow a wind associated with the radio emission. Then we have the liners associated with ADAF type and show two different types of radio regimes. The radio loud liners, which are, the radio loud liners, which are basically the scaled down version of the radio galaxies. So they behave like an FR1, like M87. And the radio quiet liners are more similar to low accretion rate Sieverts, so they're able to launch subrelativistic jet. Then we have the star-forming galaxies, where we have the non-jetted, which are classically star-forming galaxies with no evidence of nuclear activity, and the jetted star-forming galaxies. So this population of star-forming galaxies hide at the center an AGN, an active black hole, able to set an ADAF-type disk and launch a subrelativistic jet, probably like a liner. Then we have passive elliptical galaxies, which don't have any sign of optical activity, optical nucleus, but occasionally they can have a radio core on a radio jet. This is telling you that the radio and the optical phase are delayed, probably to do a recurrent nuclear activity or are starving black hole, which occasionally is fed, able to produce a disk and then launch a jet or something like that. So this is the complicated picture of nuclear activity. What is active, what is not active, it depends on whether you are looking at in optical, in radio, in the local universe. This is the C-band observation are coming up soon. This is an example of NGC 4151 in L-band C-band. As you can see, we are able to resolve the structure of the jets within 50 millisecond resolution. And this is a preliminary result of the luminosity function in C-band, where we are about a factor of 30 from Sagittarius A star luminosity. So almost there. So this is my conclusion. So LEMI is the deepest survey of the local universe in radio band, and we found this interesting break of the luminosity population of galaxies between active and inactive at 6.5 solar masses. We found complicated different disk jet coupling between active and inactive galaxies, and C-band observation are coming soon, and plenty of data we are analyzing to diagnose and understand the nature of the radio emission, of the optical emission at the center of these galaxies. And thank you for your attention.
So we are running very late. If there is any urgent, pressing question, I can take one. Anything? Okay. It's not because, but I think we are a bit tired. But let's thank our speaker again. So the next speaker. No. Cosimo Marconcini, yes, I know his name, but I just want to say it. Okay, so it's Cosimo Marconcini, accurate determination of outflows physical properties. Please, I will give you 2 minutes.
Yeah, thank you. So, good morning, everyone. My name is Cosimo Marconcini, and I want to talk to you about our new kinematical model, which is able to precisely determine the outflow physical properties. And these are the people that collaborate to this work. So, as we have understood from the recent talks in these few days, we have to include the AGN feedback in our models, basically because this is thought to be the main mechanism which is responsible to vary, to change the star formation inside the AGN host galaxies. These are some piece of evidence, observational piece of evidence that have led to claim the need for the AGN feedback. As we know, we have a common peak activity of the accretion around the supermassive black holes, but also the star formation inside the AGN host galaxies. Also, by including the AGN feedback in the models, we are allowed to basically reconcile the observations with the theoretical prediction of the stellar mass function. And finally, we think that basically because of the strong correlation which are observed between the black hole mass and the bulge properties, that like the luminosity, the stellar velocity dispersion, and the bulge mass, we have to include these features inside the theoretical prediction. But why do we want to measure the outflow physical properties? Basically, the ultimate goal is to infer the impact of the energy emitted by the black hole on the surrounding gas inside the galaxies. We have we have many observations that show us that we have very big discrepancies between the theoretical prediction and the observations, both for the molecular and the ionized mass outflow rate compared to the AGN properties like the bolometric luminosity, but also for what concerns, for example, the X-ray nuclear outflows compared to the galaxy-wide ionized outflows. And finally, we think that probably there is a strong contribution to the energy emitted by the black hole, which is interacting with the gas inside the galaxies coming from the X-ray band. So here I resume basically the main models that we used so far to infer the outflow properties. And as you can see, we have the first method, which basically derive the mass outflow rate from the simple definition of a certain amount of mass which is crossing a certain surface in the unit of time. But this method, even though it's very simple, implies that we are following many uncertainties because of the assumption that we make. And almost 20 years ago was proposed inside this second method, which is basically tries to reproduce the observed radial velocity map for the outflows by simply creating a three-dimensional model, which can be a conical one or a biconical one. Even though this seems to work very well for low-resolution observations, if we look to nearby galaxies which are observed, for example, with an integral field spectrograph, like this is the emission, the velocity map for the emission coming from NGC 7582, which is 22 megaparsec from us, we can see that basically we have a very not uniform and clumpy distribution of the gas cloud inside the outflow. So what we have to do here, we recreated the standard method results by using our model. So we created a three-dimensional conical shape, and then we assign some kinematical and geometric parameters to the cloud inside this model. We created velocity maps, and we compared to the observer one by using the standard method, and changing all the kinematical parameters until we find the best model, which is this one. And by subtracting the model and observer radial velocity map, we obtain these residuals, which, as we can see, are terrible. And this is only due to the fact that the flux emission, which is assumed, is typically an exponential decreasing one with a very, very simple radial velocity trend, which is typically a constant one, or maybe a velocity trend that peaks until a certain radius and then goes down to the galaxy velocity. So what we did was creating this new model, which is based on the fact that we have at our disposal integral field data, so with two spatial extensions and one spectral one. And then we chose a spherical coordinate system in order to reproduce the observed conical shape of the outflow. And then we projected all the clouds inside this model, which are 10 billions, in the source reference frame. So each cloud will give a contribution to the kinematics in a certain 2D position. Then, instead of assuming a certain flux function, like is typically done, we decided to measure the flux directly from the observation. So what we did was integrating the flux in every spaxel of the outflow extension, and then assign this flux to the clouds in the same spaxel. So eventually, every cloud will have a weight, which is given by the ratio between the observed flux and the total number of clouds inside the spaxel. If we look at the flux emission of our model, this is obtained by choosing the correct parameters, we can observe that this is totally resuming the observed flux map of the observation. Now, the hardest part here is basically to infer the correct parameters, as we know. And so we performed a fitting procedure, which is not based on reproducing the observed radial velocities, but just by reproducing the observed line profile of the oxygen 3 emission inside the outflow extension. So our model, being a three-dimensional model, gives us the model emission obtained from the clouds in every spaxel. And we decided to compare the model profile to the observed one in each spaxel of the outflow extension, trying to minimize the residuals. Obviously, this procedure implies that we have really a lot of degeneracies that we managed to take into account, but this is a very long process, and we can talk about this later if you want, because it takes many time. Now there's left, the slides continue. Okay. So this is the sample that we analyzed so far. These are 3 CIFER2 galaxies, which are very close to us. The farthest one is 5728, which is at 39 megaparsec from us. We performed a spectroscopic analysis in order to create the moment maps. This is the moment 0, the flux emission, and the moment 1, the radial velocity along the line of sight for these galaxies, which clearly shows a conical or a biconical outflows from the oxygen 3 emission. The results points out that here we can compare the observed moment map, the flux, the velocity, and velocity dispersion to the results obtained with our model. And as we can see, we were able to totally recover both the flux emission, obviously, but also the line profile, so the velocity along the line of sight and the velocity dispersion in each spaxel inside the outflow. On the right, we can observe the comparison between the residuals obtained with our model and those obtained with the standard method. As we can see, the residuals drop enormously compared to the standard method, and we recover the clumpy distribution of the clouds. The same applies for Circinus, and this is a very interesting galaxy because, as we can see, we have a very, very clumpy distribution of the ionized clouds inside the outflow, which implies that we cannot use a uniform flux function or an exponential decreasing one. And finally, I just want to show some preliminary results for NGC 4945, which has been already discussed by Stefano Carniani this morning. And I want to say that we are trying to apply our models not only to low redshift galaxies, but also to some quasars at redshift around 2.4, which have been already analyzed some years ago by Carniani with the toy model. So we were also able to observe the 3D cloud flux distribution inside the outflow extension. As you can see, these results, this model are very clear, and are also recovering the clumpy distribution of the clouds inside the outflows. We have no flattening on the plane of the skies, which is basically obtained by taking into account of the degeneracies. And here we have the X and Y axis, which are representing the plane of the sky, and the z-axis, which is the line of sight of the observer. Instead, the colors are basically the weight, so the flux that we observe from our subcube inductor emission. NGC 5728 can be considered basically our black sheep in our sample because this galaxy shows us that we have a strong flattening on the plane of the sky from the obtained model, but also stretched clouds in the apex position of the cone, which is the shape of our model. And this is only due to the fact that we have no reliable shell velocity in this, for these galaxies, and that this is a first clue of the need to include not only a conical shape in our model, but also the presence of the disk to take into account of the emission. These are the parameters that we'll have three in our fitting procedure, and the most important one is for sure the velocity in the shells, which we divided the outflow in. And because I said at the beginning, we want to basically properly infer the energetic of the outflow. So finally, the most important parameter and property of the outflows that we want to infer is for sure the mass outflow rate. And thanks to the fact that our model disentangled the velocity that we observe from projection effect, we were able to infer this by simply using this formula, which is the definition. So these are the results that we obtained for NGC 7582 and Circinus on the right. And if we compare this to the results obtained with the standard method, where basically we assume the velocity, as we have understood also in, in the last few talks, we assume the velocity by simply observing the line profile and then inferring the velocity from a certain percentile. As we can see, the standard method is strongly underestimating the mass outflow rate, but this applies also for all the other outflow properties, like the kinetic luminosity, in every shell of the outflows. So eventually, this will provide a total mass outflow rate, which is very low compared to our results. So to conclude, I just want to talk about our future developments, because I said before we want to include also other kinematical components like the disk. We want to combine our kinematic model with a photoionization one to better characterize the mass. And finally, increase the parameter space by letting free the parameters like the turnover radius for the velocity function, but also the inner and opening angle for our conical shape. And finally, we want not to only apply our model to low redshift galaxies, but also to high redshift galaxies where the resolution is supposed to be lower. And that's it. Thanks. Thanks for the attention.
Question for Cosimo. Okay, one, and I'm going to take that one.
Very interesting, thanks. Can you tell me a bit more about the degeneracies in the line fitting and the advantage that you get if you fit the line, I mean, to get the line profile instead of the velocity, because you said that that's one of the differences.
Yeah, that's the most important point. And casually have a perfect slide to explain this. And this is due to the fact that if we only fit basically the velocity in every pixel of the outflow extension, and this is typically done using long slit observation and not integral field data, only recently they are obtained, we lost, basically we allow for different parameters because there is a strong degeneration between the velocity in each point of the outflow extension with the inclination of the outflow with respect to the plane of the sky. So by taking into account of the actual line profile, what we do is, if we neglect the first here, this is a projection of the conical outflows, and this is the line of sight of the observer. If we neglect at first the different color of the cloud here, this is an example of the line profile that we can consider. And what we have is that if we choose, for example, a too low velocity in a certain shell, it's clear that we have a strong difference because we have some beams in the velocity space that are not properly recovered. So we have huge residuals and the model can discard this velocity easily. If instead we consider high velocity, after weighting the model, so after assuming the flux from the observation, what we obtain is that the clouds with a super high velocity, for example, 10,000 of kilometers per second, will fall above these limits. And so these are the red clouds here, which velocity projection is above the line profile. These clouds will have no contribution to the emission. So the model will assign them a zero weight, and then the model will be flattened on the plane of the sky. So basically, by looking, what we did was dividing the shell in a certain number of, dividing the outflow in a certain number of shell, and then we compute the velocity percentile at 1%, 99%. And when the model is creating, after weighting phase, what we did was basically imposing that the observed velocity, which is taking into account of projection effect, must rely in these two limits, because if we not impose these two limits, the model will perfectly fit the observed data by choosing an accelerated velocity. It would be perfect, basically. I mean, this is necessary to do.
Thank you. Let's thank our speaker again. Yes, I will give you a 2-minute warning. So the next speaker is Giorgia Peluso, exploring the IGN ramp pressure stripping connection in local clusters.
Okay. Hi, everyone. Thank you very much for giving me the opportunity to speak today. The work I will present today on the IGN ramp pressure stripping connection has been done in collaboration with the GASP team, and in particular I want to thank my supervisor, Bianca Poggianti. So, the ramp pressure stripping phenomenon is interesting for several reasons. First of all, in order to understand how galaxies evolve, it is necessary to understand the gas inflow and outflow process. So, how the gas enters and exits the galaxy disk. In cluster galaxies, in galaxy clusters, the main process is ramp pressure stripping. And it is essentially the pressure exerted by the hot intercluster medium on the colder interstellar medium. So it's like a wind blowing through the galaxy and creating this one-sided tail of gas. And the most extreme cases are called jellyfish, and they have tails even longer than the galaxy diameter. Here I show an illustrious TNG simulation of a cluster, and in the bottom panels there is a zoom on some galaxies experiencing ramp pressure stripping. They are basically spiraling towards the cluster center, losing their gas, as I said, because of the pressure exerted by the ICM. These objects are essential to understand the galaxy evolution in clusters, and they have been the focus of the GASP survey. GASP is the acronym for gas stripping phenomena in galaxies. It started like an ESO large program with MUSE. So at the beginning, it was optical integral field spectroscopy. Then some follow-up programs observed the gas even at different wavelengths. And so in order to study the molecular and the neutral gas rather than the ionized gas. And the goal of the survey is to study the gas removal mechanism acting in galaxies in different environments, so how, where, and why the gas is removed from the galaxy disk. And what are the effects on the star formation rate and the star formation history, and if there is a link with other physical processes such as the AGN activity. So if there is a connection between the gas physical condition and the activity of the central black hole. To do so, GASP collected a sample of 114 galaxies in different environments. The majority of them are in clusters, and in my work I will focus on, indeed, galaxies experiencing ground pressure stripping in clusters. These are low redshift galaxies which span a mass range between 10 to 9 and 10 to 11.5. And here I show a collection of 12 GASP galaxies. In this image in particular is obtained by combining different photometric filters in the optical band of Muse. And so you can see in white the stars. However, everything becomes much more clear when we look at the gas, so at the H-alpha emission in orange. And while I switch again between the two pictures, you can see that the stars are mostly undisturbed, while the gas distribution is highly disturbed. This is a clear sign of ongoing ground pressure stripping. So when the survey started, the very first sample of 7 galaxies had an unusually high fraction of AGN. So 6 out of the 7 galaxies had an optical AGN according to the BPT diagram classification. As we probably all know, the BPT diagrams are used to distinguish different ionization mechanisms by combining Balmer and forbidden lines to quantify the energy budget from the ionizing source and the level of ionization in the gas. In the central panel here I show one example. This is the galaxy JO201, and at the center is clear the Seifert in green, the Seifert-like emission. Few galaxies in GASP also are edge-on, like the one studied in Fritz et al. 2017, JO36. And in this case, the galaxy is heavily dust obscured, so the AGN is not visible in the optical, but can be detected, for example, in the X-ray. And as I was saying, the fraction of AGN was unusually high, even considering the fact that these galaxies are pretty massive. So an hypothesis was that this happens because the ISM is rotating and interacts with the ICM that does not rotate. And this somehow favors the inward motion of the gas towards the galaxy center because the ISM loses angular momentum, and the gas inflows can trigger the black hole activity. Some simulation have been done in the really recent years about the topic. Here I put as a reference Ricard et al. 2020 and Farber 2022, and they also show that the AGN activity in cluster is enhanced by ground pressure stripping. So, what do we need to test this hypothesis? First of all, the GASP program has today completed the observation of the whole sample. Today we have 51 ground pressure stripped galaxies in clusters, and among them we find 5 more AGN candidates that I present in Peluso et al. 2022. In these panels, you can see the 5 candidates. 4 of them have low luminous AGN, which means that they are classified as liner in the nitrogen BPT. JO171 is a Seifert, and some of these candidates have also an X-ray point-like sources overlapping the optical center with an X-ray luminosity in the energy band range of an AGN. Then, to increase the statistics, we also looked at the literature. So we listed all the galaxies known to be experiencing ground pressure stripping, and for which the classification in the nitrogen BPT of the central emission was available in the literature. In this way, we collect a sample of 115 galaxies, which is the largest sample, at least until now, presented of ground pressure stripped galaxies. Then we wanted a controlled sample of normal galaxies with same properties of the ground pressure stripped sample. To do so, we used the MANGA survey, and we selected the star-forming galaxies, so with a high specificity specific star formation rate with a late type morphology located in low mass halo, which means that we consider them to be located in the field and so presumably not affected by the stripping. To spot the AGN among these galaxies, again, we use the BPT, the nitrogen BPT diagram, and in particular, we considered the emission line fluxes within 3 arcseconds from the galaxy center. And let's say we stated if the ionization was mainly due to stars or to an AGN. And so here I put one example. I don't know if I can see. One example of the 782 galaxies. You can see that inside the yellow circle, the spaces are mainly classified as liners. And so this is one example of AGN in the manga sample. Sorry. Okay. Finally, we can compute the AGN fraction, but first we mass matched the samples. You can see in the left panel, in the right panels, that the normal galaxies have a different stellar mass distribution than the ramp pressure sipped sample. Because of that, we randomly extracted a subsample of normal galaxies with the same stellar mass distribution of the ramp pressure sipped sample, and we computed the AGN fraction in this subsample. Then, to not be dependent on the single extraction, random extraction, we repeated this procedure 10,000 times, and here I show the distribution of the AGN fraction in the 10,000 samples. And you can see that the AGN fraction in ramp pressure sipped galaxies, that is the red arrow, in the optical AGN is higher than the median AGN fraction in normal galaxies at a confidence level of 99.99/96% in 2 different mass bin. And I show here again the same fraction, but in a more schematic way. So we find that ramp pressure sipping seems to enhance the AGN activity. And even considering the mass, so the red galaxies, the red histograms are the galaxies hosting an AGN, and as expected, the AGN hosts are the more massive galaxies. However, even considering only the more massive galaxies with up to 10 to 10 solar masses, we find that the ramp pressure sipped cluster sample have a fraction of 51%, which is higher than the 35% found in normal galaxies. I want to stress also some caveats of this analysis, because in spite of the fact we took really great care to select the most homogeneous sample possible, the literature sample for this structure is dishomogeneous because the spectroscopic information come from different instruments. So a largest sample of ramp pressure sipped galaxies observed with integral field spectroscopy will be in optics will be needed. This is now not available. Today is not available. So also the AGN fraction depends on the criteria used to classify the AGN, and in this work we consider both zippers and liners because we wanted to capture also the low luminous AGN. And finally, in the literature sample, we relied on the information in the literature about the tidal interactions, so if any galaxies was experiencing tidal effects or not. So as you can understand, we didn't redo again the analysis, and this can lead to some kind of residuals. So in general, we wanted to present the best available dataset of galaxies to study the RPS-AGN connection, and to settle the basis to do better in the future. And if I have time, I want to summarize again everything. Okay, so the goal is to compute in a statistically significant way the AGN fraction in ramp pressure sipped galaxies, and to see if the ramp pressure sipping is enhancing the AGN activity. We also computed the AGN fraction in normal galaxies. To do so, we collected a sample of 115 ramp pressure sipped cluster galaxies and a control sample of 782 late type star-forming galaxies located in field, and we find overall a higher frequency of AGN in the ramp pressure sipped sample at a confidence level of 99.96%. Also, the AGN hosts in the ramp pressure sipped sample are in the info region of the phase space diagram, which is also the region where the stripping is the most intense. So also this result is, let's say, consistent with the hypothesis of a connection between the two phenomena. And with this I will stop. Thank you very much.
Questions?
Just a curiosity. So you have 782 in the control sample, no? And you extract 115 as the sample you want to test, no? Mm-hmm. And every time you extract, you're checking that the distribution is different, right?
No, when we extracted in order to have the same distribution. So, for example, the rampers...
Okay, I'm saying from two different extractions, the distribution is different. Did you check also this?
No, the distribution is not. The galaxies change. The galaxy extracted change because they are more than the ramp snippet sample. But the distribution is the mass distribution is fixed. It has to be the same.
Okay. In other words, is there the chance that you are extracting randomly out of the 10,000 two very similar ones?
Ah, okay.
Did you check this?
Okay. No, we didn't check this because this is we did it randomly. We didn't. No.
Okay.
It was. It is like this free bootstrap. It is something left free.
Okay. Thanks.
If it is very quick, yes or no questions, while the next speaker would be on stage. Is not. Okay. So we are very, very late. Okay, thank you very much. Let's thank our speaker again.
Spoiler.
Wow. Let's see the entire talk before. Okay. Giacomo Venturi with AGM feedback from Galactic ions, outflows, and etc.
Yeah, so good morning. I'm Giacomo Venturi. I'm a Fondacy postdoctoral fellow at the Universidad Católica in Santiago de Chile. And in my talk, I will present you our study on the effect of low-power jets on ionized gas from VLT Muse. So you already heard a lot about the reasons for the need for feedback, but just to say it another time, it is invoked to explain many observed properties of galaxies. And most importantly, one of the most important one is the lack of massive galaxies in the galaxy luminosity function, the high mass end. When you compare observations and predictions from cosmological simulations, if you include feedback, you can reconcile theory and observations. So clearest observational evidence for AGN feedback comes from powerful jets in the so-called kinetic mode feedback. So in this case, you have these powerful jets around the massive brighter cluster galaxies, filling the X-ray halos around these galaxies, keeping the halo hot and preventing accretion on the galaxy and further star formation. So you can see two clear examples here. So these powerful jets are also capable of accelerating massive outflows, and in this traditional picture, jet feedback is exerted by powerful and very extended, so tens hundreds kiloparsec jets in radio loud AGN. But what about the role of low-power compact jets? So they were once considered not very important, but there is growing evidence from recent observational work that also this low power, so below 10 to the 44 erg per second of kinetic luminosity, and compact, so only kiloparsec scale jets hosted in radio-quiet sources are able to affect their host galaxies by pushing outflows. So we can see a couple of examples where outflows are observed in the direction of the jet propagation from blue shift and asymmetric emission lines. So in our study, which we published in 2021, we investigated the role of low-power jets on the host galaxies in 4 nearby Cipher galaxies, so below 50 megaparsec, observed with VLT Muse from our Magnum survey, about which Giovanni talked extensively yesterday. And so all these four galaxies host a low-power compact jet. Here you can see them. They're pretty famous galaxies. You can see the Muse field of view covering 1 square dark minute of the central portions of the galaxies. So here are the Muse multicolor maps. You can concentrate on the green, which is the oxygen tree, tracing the AGN ionized bicons. Here, for reference, the axis of the AGN ionization cones. If we investigate the maps of the O3 line velocity width, on which we superimpose the radio jet contours in black, you can see that the radio jets are aligned with the AGN ionization cone axis, but the O3 line velocity width is strong, is enhanced in the perpendicular direction to jets and ionization cones. So this is surprising because usually you expect normal classic outflows in AGN along the AGN ionization cones. So as for this example of NGC 1365 that we published in 2018 and Giovanni talked to you about yesterday, you can see the O3 cones in this direction and this biconical outflow in the same direction with this strong oxygen 3 line velocity width and traced by asymmetric wings in the emission line profiles. So even in these four galaxies that I was showing you, there is a classic outflow in the direction of the AGN ionization cones, actually, traced by asymmetric wings in emission lines with a coherent velocity on each side of the nucleus, so either blue shifted or red shifted. But the material in the perpendicular direction has very different properties with very broad and fairly symmetric line profiles, so suggesting a different origin for the gas in these two directions. Okay. This gas in the perpendicular direction with large velocity dispersions also exhibits from the spatially resolved BPT diagrams a shock-like ionization, as also indicated by the comparison with the grids of shock models, as you can see here. So what do simulations say about the interaction between jets and galaxy disks? So they say that there is an effect of inclination. So these are simulations of interaction between jets and clumpy ISM in disks. So you can see that when the jet is perpendicular to the galaxy disk, there is weak or no interaction, and the jet easily escapes the disk. While instead, the jet is at low inclination, with respect to the galaxy disk, as you can see from this movie, the jet remains trapped in the disk and struggles to propagate, and so creates a lot of mass, induces shocks and turbulence, and increases the line velocity dispersion, generates turbulence in the direction perpendicular to its propagation. We also investigated if there is a relation between the ionized mass and kinetic energy of the gas having this large velocity dispersion perpendicular to the jets and the jet power. We see that though these are only 4 objects, so it's not very statistically significant, but they seem to correlate. So seems to be a correlation between the jet and the gas mass affected. But most importantly, if we compare the kinetic energy of the affected gas with the energy injected by the jet during its lifetime, we see that the ratio is much smaller than 1, so indicating that the jets are easily capable to inject the required energy into the ISM, even with a low energy transfer efficiency. So summarizing, what seems to be the most likely origin for this mechanism, so for this perpendicular line velocity dispersion enhancement, so perpendicular to jets and AGN cones? So all these galaxies exhibiting the phenomenon have in common that they host a small-scale, low-power jet. These jets are at small inclination, so below 40 degrees compared to the galaxy disk plane. So we saw this leads to a strong jet-ISM interaction. So the gas in the perpendicular direction showing the line velocity dispersion enhancement has very different line profile properties compared to the classic AGN narrow line region outflow, so suggesting a different origin, a different mechanism originating the two. Also, this gas in the perpendicular direction has a shock-like ionization, and as we just saw, the jets are easily capable of injecting the required energy into the ISM. So it seems that the most likely origin for the phenomenon is the interaction between the jet and the galaxy disk material, perturbing and shocking the ISM and driving this turbulence perpendicular to the jet propagation. So then, this is the teacup AGN. So it's a quasar. It's a very different object compared to the nearby Seyferts that we saw so far. It's a low redshift quasar, so a much higher radiative output, so above 10 to the 45 ergs per second, where the Seyferts before were like below 10 to the 43, 10 to the 44 ergs per second. And it's radio quiet again as them. So this is a very complex source. You can see it hosts this peculiar oxygen-3 bubble, giving the galaxy the name teacup because it resembles a teacup handle from which you drink tea, right? It has a very extended narrow line region that you cannot see in this image, but I assure you is there. So it's a 100 kiloparsec narrow line region where this bubble is 10 kiloparsec. So despite being radio quiet, it hosts two characteristic and extended radio bubbles co-spatial with the O3 loop, with the O3 bubble. If we investigate the high resolution radio data, I don't know if you can see with the contrast, but there is a small scale compact jet, 1 kiloparsec size in the middle, having a low power. So again, if we look at the line velocity dispersion of this galaxy, surprise, surprise, we find that, again, it is enhanced in the direction perpendicular to the jet and ionization cone axis, as in the Seifert galaxies that we saw before. And has an ionization compatible with the presence of shocks, as indicated by the BPT diagrams. So, sorry for this. So, in Lorenzo Levy's master thesis work, he analyzed some other luminous quasars at low redshift, so with AGN luminosities and redshift similar to the teacup that I just showed you. And he found, so these are again Muse data, he found that perpendicular to the jets and the AGN ionization cones, so the jets here are traced by the green contours and the O3 emission is the grayscale map, he found again an enhancement of the velocity dispersion in the perpendicular direction. So this large gas velocity dispersion perpendicular to jets are observed also in quasars, not only in nearby Seyferts. So the jets are able to induce this phenomenon also in more radiatively powerful sources like quasars, where you wouldn't expect these low-power jets to be important. You would expect the radiation to be the dominant factor, but still the jet seems to have a role to impact the host galaxy. By looking in literature, you actually found that this phenomenon is observed in many other objects. You see all the references here. And this line velocity dispersion perpendicular to jets and ionization cones is found in all these sources, which again host the same properties as those that I show you in the talk. So they have low inclination with respect to the galaxy disk jet, compact and low power. So it seems that this may potentially be a widespread phenomenon and potentially constitute an additional channel for AGN feedback to be taken into account. So this turbulent gas may mix the ISM and enrich the CGM if this turbulence is actually perpendicular to the galaxy disks as suggested by simulations. And it could hit the ISM and damp star formation, or at the same time even compressed clouds and foster star formation. So a combined negative and positive feedback mechanism as suggested by very recent simulations. So we should investigate these aspects. And so I leave you with my conclusions, and thank you very much.
Fabrizio.
Thank you very much. Up to which distance on the disk can this mechanism work? I mean, up to which distance you expect evaporating gas to the halo?
Okay, so I can tell you from the observational point of view, these are several kiloparsec scales. So this is what is observed. And yeah, the simulations also predict that the scales would be kiloparsec scales. I mean, from the observational point of view, it obviously depends how much sensitive you can be to detecting these features. But yeah, I want to stress that from these observations, we are not sure if this gas is actually perpendicular to the disk, as simulations predict. We are not able to tell this for sure. Yeah.
Let's thank our speaker again. And the next speaker is Carolina Andoni. I don't know if I pronounce it correctly, to be honest. Carolina? Yes. Carolina.
Okay.
And I will give you a 2-minute warning. So
wait, who can?
Yeah. Okay.
Yes.
Okay. So with fundamental differences between obscure and non-obscure quasar in the cosmos field.
Hi everyone, I am Carolina Andoni, a PhD student at Durham University, and I am so part of the Buy4Best training network. My main supervisors are David Alexander and David Rosario, and today I will talk about my work on fundamental difference between obscure and non-obscure infrared quasars. Okay, so as all here we know, the AGN orientation model tells us that the orientation of the dusty torus with respect to us influences the observed properties of obscure and unobscured AGNs. But we expect that after correcting by the effect of descuration, the fundamental properties of both obscure and unobscured AGN should be the same. However, recent investigations in your group have found a fundamental difference between red and blue quasars, which cannot be explained by the AGN orientation. As a fast overview, blue quasars are really bright objects that are blue in the optical band because we have an unobscured view of the accretion disk, and red quasars are objects that are red in the infrared and in the optical because that's extinction in our line of sight. So again, we would expect to, after correcting by that extinction, both red and blue quasars should have the same properties. But this recent investigation in our group have found fundamental difference in the radio properties of red and blue quasars, where red quasars have an enhanced radio emission compared to blue quasars, with 3 times more radio detections coming from radio compact radio emission in subgalactic scales. So the conclusion here is that red and blue quasars are actually different phases in the evolution of galaxies, where red quasars are a younger phase in the evolution, and they have an enhanced radio emission, likely due to small-scale jets or AGN-driven outflows interacting with the circumnuclear dust and gas via chokes. So, in order to extend the research on red quasars to the most heavily obscured systems, we select a highly complete sample of infrared quasars in the cosmos field. We feed the UV to far infrared spectral energy distribution using the Fortes feed, and select all the sources with an AEL luminosity higher than 10 to the 45 per second and a redshift lower than 3. To fit the SED, we include the accretion disk emission, the unobscured stellar population emission, the dusty torus, and the dust-obscured star formation. And we found 544 infrared quasars in cosmos with a redshift lower than 3. So now the main question of this study is how the properties of obscure and unobscured infrared quasar compare. And to answer that, we investigate the radio properties of the sample, the star formation properties that we obtain from our SED fitting, and the radio emission. So to study the X-ray property of the sample, we use the published X-ray spectral fitting results in the Cosmos field. We found that around 60% of the sample is detected in the X-ray, so those are 329 sources, and 91 from those 329 sources are obscured by column densities higher than 10 to the 22. The other 40% of the sample is X-ray undetected or X-ray faint. This means that they are X-ray detected, but they don't have enough counts in the X-ray band to perform X-ray spectral fitting. So we assess the level of obscuration of these sources using X-ray stacking. You here can see the stacked images of the X-ray undetected sources in the soft band between 0.5 and 2 kV, and in the hard band between 2 and 8 kV. And you can see that in both cases, we got a really strong signal, suggesting that the X-ray undetected and faint sources are undetected because most of the X-ray emission was absorbed by these heavily obscured column densities and not because they are intrinsically faint. Then we use the hardness radio, that is defining function of the cones in the soft and in the hard band, to assess the level of obscuration. Here we show the change of the hardness radio with the redshift for two different column densities, 10 to the 22 and 10 to the 23. And you can see that on average, the X-ray and undetected and faint sources are located on a region of the plane that is affected by heavily obscured column densities higher than 10 to the 23 square centimeters. In addition, we also use the relation between the intrinsic X-ray luminosity and the 6 microluminosity coming from the AN to also assess the level of obscuration of the X-ray undetected sources. In this plot, well, the blue stars are the X-ray detected sources, and the black upper limits are 3 sigma upper limits for the observed luminosity of the X-ray undetected quasars. We also plot the two intrinsic relations from Stern and Fiore, and we plot the same relations but affected by a obscuration of 10 to the 23 and 10 to the 24. And you can see that most of the X-ray undetected sources are located on a region of the plane affected by Compton thick column densities, like around 10 to the 24. So using this Vota analysis, we are quite sure that most of the X-ray undetected and faint sources are heavily obscure. So, and likely comprise the most obscure subset of infrared quasars in the Cosmos field. So from now, we split our infrared quasar sample in the obscure sample and unobscure sample, and we use a column density of 10 to the 22 as a threshold. So this is a composite UV to far infrared SED of infrared quasars. The thin lines and the individual SEDs of each quasar, and the thick lines are the median SEDs. So the continuous thick lines are from the obscured quasars, and the dotted thick lines are for the unobscured. The black lines are the overall SED, and we also plot the relative contribution of the different components of the SED to the 6 microluminosity. So we can see that clearly both SEDs for obscure and unobscured sources are different. As expected, of course, in the optical band of the SED, the median SED of obscure sources is extincted. But the most intriguing difference are that first, the star formation component of the obscure sample is stronger, and also the torus component of the obscure sources is cooler, having more far infrared emission and less mid-infrared emission. So in order to investigate this difference, we now compare the properties of both samples. So, well, we found that obscure sources have an enhanced star formation rate compared with unobscured sources. We found this after matching both samples in redshift and AEL luminosity. In particular, we found that obscured quasars have, on average, star formation rates 2.6 times higher than unobscured quasars. And also, they have more Herschel detections than unobscured quasars. And this last result is completely independent on the SED fitting. Here we plot the distribution of the star formation rates in black for the obscured sample and in magenta for the unobscured sample. And it looks like that the obscure infrared quasars have a population of starburst galaxies that the unobscured quasar sample doesn't have. We then investigate the radio properties of the sample. Here the left plot shows the 6 microluminosity coming from the AGN that we obtained from our SED fitting versus the 1.4 gigahertz luminosity, and the red line shows the separation between radio quiet and radio loud sources. And well, you can see that most of the infrared quasars are in the radio quiet regime. We then investigate the origin of the radio emission using the Q parameter that is defining function of the radio of the far infrared luminosity coming from the star formation and the 1.4 gigahertz luminosity. And we plot 3 different relations that say when the radio emission is dominated by star formation processes. And we found that for the 80% of the sample, the radio emission is dominated by the AEN. So basically, the radio emission of most of the infrared quasars is in the radio quiet regime and dominated by AEN processes. So then we compare the radio luminance of the obscured and unobscured sample, again after matching with redshift and AEN luminosity, and we found that the radio luminance of obscured sources is 0.2x higher than that of unobscured sources, and also that obscured quasars have 1.2 times more radio detections than unobscured quasars. So what is the origin of this difference between the obscured and unobscured sample? As most of the radio emission is radio loud and is originated by the AEN, we believe that this is probably the radio emission originates by the interaction of small-scale jets or AEN-driven outflows with the circumnuclear gas and dust. So via chokes, when the outflow choke with the gas and the dust, produce synchrotron emission, so it has an increased star formation, so increased radio emission. The small-scale jets or outflows can also explain the suppression of the star formation rate in an obscured system, as we know that this can produce negative feedback. And also, if we come back to the composite SED, the AEN-driven outflows also can explain that the AEN has the median AEN SED of obscured sources is cooler, because it's been shown that AEN-driven outflows can create an extended component in the polar direction that is cold, and it peaks at far infrared wavelengths. So, summarizing, if you want to put in context or result in the AEN orientation or evolutionary model, we think that they are not consistent with an AEN orientation model, as we found fundamental difference in the radio properties and star formation properties of obscure and unobscured system, and they are probably more consistent with an evolutionary or transition model, where obscured quasars are a younger phase in the evolution of galaxies, and where both the supermassive black hole and the host galaxy are undergoing a process of rapid growth and probably hosting really powerful winds, while unobscured systems are a later phase in the galaxy evolution, where they have suppressed star formation, likely due to the interaction of these small-scale jets or wind with the interstellar medium that blow out the gas and dust or heat it. So, well, these are my conclusions, and thanks for the attention.
Questions?
Thank you very much for the talk. It has been very interesting. Thank you, Carolina. Maybe you said that and I just missed it. When in the object there are and that you detect in X-ray and that you have X-ray faint, do you analyze them in terms of obscure and unobscure altogether?
Yeah, of course. The unobscure sample is only comprised by sources that X-ray detected, and they have a column density lower than 10 to the 22. And the obscure sample is composed by the X-ray detected sources with a column density higher than 10 to the 22, and the X-ray undetected sources. Of course, not all the X-ray undetected or phase sources are heavily obscure, but on average, they are. And we compare just the properties of the obscure sources that X-ray detected and undetected and are practically the same. So we are really confident that they are obscure and they are real agents.
Perfect, thank you.
Let's thank our speaker again. And the next speaker and last of this scientific session is Federico Esposito, with IGN impact of molecular gas in the Galactic Center as probed by CO lines.
Okay, can you hear me? Yes. Okay, thank you for inviting me here. And I'm Federico Esposito. I'm a PhD student in the University of Bologna, and my work is on the AGN impact on molecular gas in a sample of local AGNs, as probed by carbon monoxide lines. And my work is supervised by Livia Vallini from Scuola Normale Superiore in Pisa, and Francesca Pozzi and Viviana Casasola from University of Bologna and INAF sections in Bologna. So we started this conference with Ivan Del Vecchio reminding us the importance of molecular gas for the AGN galaxy coevolution, as also shown by this famous plot. And molecular gas is also very useful for tracing, at this moment with ALMA observation, the young interstellar medium at the beginning of the history of the universe, as shown by Antonio Pensabene talk on Monday. And is also useful for studying the AGN obscuration, as shown by Francesco Salvestrini and many others in this conference. And we expect, of course, feedback between the AGN and the molecular gas. And feedback can be negative, and there are plenty of evidences for this, but can also be positive, as shown by, on Monday, Quirino D'Amato, but also many others also today. And there are mainly two modes of this AGN feedback. One is the mechanical feedback, in which shocks hit the molecular ISM. But I will focus on radiative feedback, and especially on the effect of X-ray photons on the ISM, in which X-ray photons create X-ray dominated regions in the ISM, and this can be studied fitting the CO's LED with XDR model and compare them with PDR models mainly. So this is an example of a CO's LED, which is a spectral line energy distribution of the CO rotational lines up to the CO 1312. Mainly, our interest is in the high J part of the CO's LED, because this is the main part affected by X-ray photons. And this has been observed only in the local universe by Herschel. And so what we did was to collect from the literature luminosities of this CO's LED observed by Herschel, and select only the galaxies with X-ray luminosity, intrinsic X-ray luminosity over 10 to the 42 erg per second. And also we collected 70 micron images for these galaxies, and ALMA CO625 images when available from the ALMA archive. So this is an example of some optical images of the galaxies we selected. The final sample is made of 35 local AGN, and you can find the full list on the paper that has been recently published on MRAS. So the first thing we did, since we had the CO120 and the star formation rate from the 70 micron images, was to put our galaxies on the star formation rate and molecular gas surface density, studied by the Schmidt-Kennicott mainly. And our galaxies are the blue stars. The blue circles are another AGN sample, while the gray symbols are all non-AGN galaxies. And what we found is that on the scale on which we studied this, which is mainly kiloparsec, few kiloparsec, there is no evidence of an AGN effect, as also shown by Francesco in the talk of yesterday. So we thought maybe we should focus more closer to the AGN, and how much we decided it using the ALMA CO625 images. So this is an example of the data that we gathered. This is for NGC34, and on the left is an optical HST image, which is several, I think, 20 kiloparsec wide. And the large white circle is the CO625 Herschel spatial resolution, which is very large. So it doesn't allow us to understand how large is this, how large is the size that this emission is originated from. While with the image from the ALMA archive, there are two contours at high and low resolution for these galaxies. We could constrain the size to be, in this case, around 300 parsec, and on average for the galaxies that we have this observation from for our sample, we found an average size of a radius of 250 parsec. So we focused on this radius, 250 parsec, and we assumed also that all the Eiger J lines, which are not available in the local universe with ALMA observations, also originate within the same radius. And so within this radius, 250 parsec, we wanted to compare the far ultraviolet and X-ray incident flux on the molecular gas, which created respectively PDR, photodissociation regions, and XDR, X-ray dominated regions. This is a sketch of an active galaxy. And in the center you can see the AGN creating around it an X-ray dominated regions, and all spread all over the galaxy, PDR surrounding star-forming regions. For the PDR incident flux, which is far ultraviolet flux, we used the 70 micron image, the 70 micron radial profile we gathered, and we converted it to a far ultraviolet flux, which is a G0 in units of a Hebing field, just assuming that all the 70 micron photons are just photons, far ultraviolet photons reprocessed by dust at 70 micron. While for the X-ray flux, we just used the intrinsic X-ray luminosity and divided it by 4 pi r squared. So this is the result that we have. Basically on this plot, on the left side, on the left panels, on the x-axis there is the far ultraviolet flux at 250 parsec, while on the right panels there is the X-ray flux, so this is for PDR and this is for XDR. And on the y-axis is the line ratio between these three lines, CO9 to 8, 11 to 10, and 13 to 12, just to take three sample lines at IJ, and on the denominator there is the CO6 to 5. So every little square here is one of our galaxies. The blue symbols are for detections, and the red symbols are for non-detections or upper limits. We fitted these symbols with a regression line, taking into account detection and non-detections. And what we found is that all the slopes have sublinear, all the lines have sublinear slopes. And so our conclusion was that neither PDR nor XDR heating is actually dominating this CO line ratio, and that probably a mix of the two is necessary. We also had already available from Livia Vallini, my supervisor, some cloudy models for PDR and XDR. And so we decided to superimpose these models to these plots. So these are the same plots, same axis, just I took off the regression lines, and superimposed are the cloudy models at different gas densities. So the gas densities range from 10 to the 2 for yellow and up to 10 to the 5, 10 to the 6 for the dark blue. So for the PDR case, we find that the PDR models need extreme densities, like over 10 to the 5 centimeter to the minus 3 to reproduce the observed CO line ratios. While for XDR, lower densities are needed, but the results are degenerated Eiger J. So our final conclusion was that a mix of the two probably is needed, but at 250 parsec maybe is not very clear this. And so these are my conclusions for this work that have been published recently on MNRAS. So when we see the effect of the IGN on the large scale, it seems that nuclear activity is not impacting the molecular gas, as seen on the Schmidt-Kennigat plane. And when we compare the observed far ultraviolet and X-ray fluxes or the cloudy simulations, it seems that PDR probably is not dominating, and so a mix of PDR and XDR is necessary, or some other mechanism like mechanical feedback by shocks is needed. So what we are doing right now is try to perform new cloudy simulations, and actually our model is a bit more complicated than these single models that are depicted in the previous plot. And so the new simulations are just PDR and XDR simulations with this grid setup on density and incident flux. But the philosophy is now that every cloudy run is a single clump within a giant molecular cloud, and single clumps are extracted from a log-normal density distribution, which is set up by turbulence, as proved by many observations and simulations. And this work has been inspired by previous work by Livia in 2017 and 2019. And so what we are trying to do is to link the radial profiles that we collected. This is an example for NGC 7582, which has been nominated just a few talks ago. And we are trying to link the incident flux that giant molecular clouds see from far ultraviolet and X-ray, and the molecular mass radial profile from the CO1 to 0 observation. And this is some first promising result for this galaxy, for example. For some other don't work so good, but for some, yes, and we are trying to perfect it. So this is the observation of the CO SLED for this galaxy in black, and the three colored lines are for three different models of giant molecular cloud. The dotted part is for PDR, the dashed part is for XDR, and the solid lines are just the sum of the two. So this is just a summary of my past, present, and future work. Basically, in this paper published by MNRAS, we have studied radiative feedback observation on this sample of 35 AGN, and what we concluded is that at 250 parsec of radius, probably a mix of PDR and XDR is necessary, but we are limited by the high J CO lines spatial resolution. So we are trying now radiative feedback simulations with this model that I described you, and also linking the simulation with the observation we gathered, and new observations that are coming from the FANG survey for some selected targets, and they studied the molecular gas distribution with unprecedented detail in nearby galaxies. And next I will also focus on mechanical feedback, collaborating with Almudena Alonso Herrero and Santiago Garcia Burillo in Madrid as part of the GATUS survey, with observation and modeling of this feedback mechanism too. So thank you for your attention, and thank you for all this great conference.
Questions? I can see one.
Very quick question of curiosity. We know that cloud is very accurate, as accurate as we can build a photoionization code for ionized gas. But it's not clear to me, I don't know really, how accurate can we consider cloudy for the prediction on molecular lines? Do you know, is there anything in the literature about that, or do you know anything about this?
Yeah, there are several works that actually use the CO SLED compared with cloudy predictions, and they have been also compared with other radiative transfer codes, as the UCL one and some other that now I don't remember. But the works that I was quoting at the beginning by Francesca Pozzi and Matilde Mingozzi, they used all cloudy, also by Livia Vallini. They all use cloudy with the molecular observations. And they actually agree with other codes that are trying to do the same.
So let's thank Federico again.
Thank you.
Federico and all the speakers and attendees of this week, because we are at the end now.
That's my turn. Oh boy. So, we are at the end, and on top of all this, I was given a task to do the concluding remarks. And I'm not introducing myself. I guess you've seen me around a little bit these days. And I've been trying in the spare time to study all your talks, but let's see what I can do. I'll be brief because we are late and I'm sure you want to go home to catch a train or anything. And I'm not saying anything else, but this conference has been quite a journey. And I just want to recap a little bit what happened during these 2 years. So let's see if I can use this as well. So the organization of all this started in October 2019. The venue here, the Facoltà Teologica dell'Italia Centrale, was already decided back then. The dates, which you have heard, when we sent the first announcement, were in October 2020, then circulated on January 2020. Reviewers were invited. Everything was all set, and then we have to suspend everything. The reasons you know, we postponed the meeting due to COVID. The apocalypse happens, we were locked down, and we had to postpone. We didn't know, actually, how the situation was. Further delay by 1 year, new first announcement on November 2021, and the meeting finally brought forward until May. Paolo already explained what Renaissance means, and it has several meanings. It's not only because of the venue, which is Florence, and so the Renaissance, but also because we want to stimulate and foster discussion within the IGN community that has been not silent, but we haven't had the chance to meet with each other in these 2 years. So Renaissance has several, and probably more profound meaning than the word itself. We had these are the 4 main scientific topics of the conference, as you know, and just a little bit of statistics. I just want to try to understand what we've been dealing. So we had 6 invited reviews, and in green you can see our last AGN conference in Milan, AGN 13. So 6 invited reviews, there were 11 on the next conference. We have 79 contributed talks, 49 in the previous conference, 33 posters and 30 flash talks, and we had 120 requests for contributed talks. So the SOC has had really a little bit of work trying to accommodate as much the contributed talks within the schedule. We have 170 registered participants to this conference, and the final attendance has been roughly 145 people. We had 16 participants from here, and what I called 15 truly international registrations, so people that are coming from abroad and that are really coming from abroad, from UK, from Spain, Greece, and South Africa, etc. So the IGM conference has become truly international. And as you can see, all of these locations, we didn't know if the location could accommodate all of you. Post-COVID Renaissance and all the changes in the COVID restriction, which we had and we didn't have anymore. The internationalization of the audience, everything combined was an explosive compound. And I have to say that none of this could have been possible without the great, great help of the people down there, which I really want to ask you if you can just come. So Patrizia Braschi and the people from the venue. Graziella Federico. Francesca Bulleri. So This big applause is just for you because you have been so kind with us. Patrizia has been my angel through these days. They have been patient. We were quite a big crowd for the facoltà. I think you have perfectly solved the stress test. And Alessandro, which I don't see, where is Alessandro Burgen? Where are you? Okay. So Alessandro was the man behind the scene, somewhere in here. I asked him to come, but well, a big applause to Alessandro as well. I'm sure he will listen. So thank you again. So, I've been running quite a bit back and forth this room, but I try to make a scientific and I'm not going to hide it, highly biased summary of the scientific result that I heard during this conference. I try to list a few of them, and please, a disclaimer, don't get offended if you don't see your name, you don't see your favorite result. It's not because it's not important. Every single talk was important. It is a piece within the big scheme. He's just, I'm just a human being, I guess. So, let's start with the first one. So we started with the black hole galaxy convolution and environment. And one of the results that caught my attention was the water measurement. And I think that was quite interesting. And I was quite amazed by the tightness of this relation, probably because I'm not in the field. So I say, okay, that is quite interesting. And another thing that really caught my attention was this. So what CO dynamics can do for you. And Lely showed us that you can measure black hole masses with a decent accuracy with CO dynamics. And then we have also the measure of the black hole mass in dwarf galaxy, which is the smaller black hole mass, to the record, I guess, in a dwarf galaxy. And I'm just going to go through them. So another thing which was quite new is the dual AGN. So this topic, I think, is going to become more and more common. We had just a couple of talks about it, but the technique that was devised by Filippo Mannucci and also Alessandra De Rosa gave a nice review on the topic, showed that we can probably select candidates, like dual or binary AGN candidates, thanks to Gaia. So these may open an interesting research path on binary AGN. And yeah, I think this is quite interesting and quite new. So hopefully we will have more in the next AGN meeting. Outflows. Outflows. I think this is one of the most used words in this conference. And not only in this session. I think 99% of the talks have used this word at least once in a slide. I was just running through them. And outflows is really one of the things that all of you have been working on, all of us. And even Rosita entering into the outflow. Oh, there you go. That's him, Alessandro. The man behind. So we had, this is really a non-comprehensive list of people. Outflows has been really a topic that were, I'm not going to say dominant, but pretty much in every single session. And we have been heard today, and let's try to put one slide from today's session about outflows, which was the talk by Emanuele Bischetti that showed us this first systematic search of broad absorption like outflows in redshift 6 quasars. And I was quite intrigued by this could be the epoch of the onset of the galactic evolution at this stage. I don't think we have an answer yet, which is good because there is still work to do, but probably we can move on from here and then make more more robust statement if the sample can be enlarged. But in any case, outflows, and then jets. I think together with outflows, even jets were actually quite, the audience was quite vibrant and excited about the jets in all flavors. And I'm just, I was intrigued by these new samples of restarted radio galaxies. So the jet that turn off, and then you can measure the duty cycle of the jet. I think this is a quite interesting topic, and there are several people working on this. So let's see what. Now we have this new sample. Let's see what the results will be in the next AGM conference. The next AGM conference you will be attending. Wow, I couldn't hold myself. I had to put this picture again. This is just beautiful. At long last, we have another. We have the let's say image of the black hole of our own galaxy after M87. I think it's just beautiful that we can do such a detailed work on such a detailed image on something. Well, these are quite nearby, but and we can learn so much stuff on the black hole, like spin or the direction of the jet. I was quite intrigued. I mean, my question was how the jet can be parallel to the disk, while we know that the Fermi bubbles are perpendicular to the disk itself. I think this is quite. I mean, I don't have an answer to this question. I don't know if, and talking with Elisabetta, I don't think they have an answer either. So I think this is quite puzzling to me. Changing look. I remember on the last conference, on the several years ago now, on the AGN 13 in Milan, the changing look were a topic which was quite new. Now there are changing look AGN at all wavelengths, from UV to X-ray, and now radio as well. So we have also changing look AGN at radio wavelengths, and Vanessa showed us this another class of changing look AGN. So this AGN then change from type 1 or type 2 or whatever that means for radio then, also at this wavelength. So this is another bit of the puzzle that needs to be solved. And then, last but not least, high redshift quasar. This is all the topics are the future. This is one of the things that actually I kind of enjoyed it very, very much. And I think that these images of 100 parsec resolution by ALMA are just beautiful. And this was shown by Roberto during this review, that we can reach such an amazing resolution with ALMA. And then just recapping here, because I think this is quite interesting, what we can learn from high redshift quasars. So we can measure the amount of H1 in the epoch of reionization. It has been found that there are large-scale over densities, companions, and then some X over there, which means that it's something that still needs to be solved, some issues that needs to be solved. So I found this summary slide quite interesting and nicely done. Well, it's not only science, but open issues, which is good because it means that we have work to do. And, well, I couldn't hold myself. I also had something on the LX LUV, which I'm sure you are bored to listen, but I'm just saying again, we know that this relation from an observational perspective, but we do not know much about the physical meaning of this 0.6 slope that we all love. Black hole sees a high mass, a redshift higher than 6, and we have heard that detecting the Ross galaxy will be a challenge even for JWST. The nature of dark matter, particle versus black hole, and everything you want to know, you have to ask Nico Capelluti. Also, this was for me quite interesting. The Hyperion sample, Luca showed us what you can do at Redshift 6 and what you can learn if you give 2 more plus megasecond with XMM. Let's see what the rest of the data will look like. We have seen the first radial outbreaks at a high redshift where the jet seems to change direction. Could have been the case also for the Sagittarius A star, given the differences from the Fermi bubble and the jet orientation from the data. Who knows? And last, what is driving the outflows? And this is one of the questions that I think Fabrizio asked during the outflow session before the coffee break. What is driving the outflows? If there is any connection between the small traced by the X-rays and the large ionized and or molecular scale outflows. So this is my highly biased summary, and I'm sure it's not comprehensive and not satisfactory by all means, but it's not being a science, or at least 99% science, and then the drama happens. We have these people before, and now some of them didn't quite, well, they are here. They are fine. They are good. But I hope you have fun at the football match. I wasn't there, but I see lots of smile faces. So, yeah, as I said, this is before the drama. I don't have anything after the drama. Or, the highlights from the football match, I don't have much. But I have lots of highlights from the social dinner, which was quite explosive, to be honest. But lots of smile faces. There was quite a bit of food. Hope you enjoyed it. And this is also within the conference, also the fact that we were all together finally after a few years, and we can have a nice supper together. That was quite good. I enjoyed it very much. Hope you enjoyed it as well. So, move on from here. So have you seen the slides that were flashing during the breaks and during the switch from one speaker to another sometimes? So we are in Florence, and this is the IGN 14 conference. And I want to thank all of you for the great talks. It's not rhetoric, it's true. And I want to thank in particular the students, PhD students. During the conference, I was stopped by a few of them, and I think they made me quite emotional because for them it was the first talk after 3 years of being locked down at home and having their PhD done with a supervisor on bidimensional, on Zoom, Skype, or Slack, or whatever social media or platform you can think of. So I think for you, hopefully that for you in particular was a fruitful conference. Move on from here. So we say goodbye to Florence, and we want to, you all know where the next Asian 15 conference will be in Padova, and these are the 2 reference people from now on, so my job is over. And I thank you also on my side, so I'm going to leave the floor.
Just a final word to thank you all again. But most important, I think maybe you agree there is one last person we have to thank, right? Who is he? Who is she? Yeah. So thank you, Beta, of course, and also to Emanuele and Paolo Tozzi, who is not here today, but, I mean, he will hear us. So thank you again. Bye.
Have a safe journey back home.
Grazie per tutto, no? Ci vediamo.